monopole is this printed strip that resides on a thin layer of FR4 that rests on top of the frequency selective surface. This is the back side. You can see all the soldered vias. This is the front side without the element. The total thickness of the structure is about 153 mils, and that's with the solder, and it's about roughly a 90th of a wavelength at the lowest frequency of interest to us, about 860 megahertz in this case. And again, inside is the magnetically loaded material that's about 100 mils thick. Here's a case for the shorter 2-inch bent wire monopoles. In this case, all the shorter monopoles were tuned with a tuning cap at their end. The feed port over here, and all the, as shown in this case, and in all the remaining or other antennas, was the center conductor of an SMA connector. Again, the sizes are all the same, about 2 by 4 inches, and the thicknesses are all the same. In terms of performance, this is the interesting part. The return losses are shown on the left. Antenna efficiency is shown on the right. Efficiency was measured in a CETIMO range in Laurel, Maryland. In fact, it's the old E10 CETIMO range. The interest to us is shown in terms of frequency range is the green box, the GSM 850 and 900 bands. And we see here that efficiencies for all three cases are shown. The black is the 40% loaded HQ material. The red below that or near that is the 50% loaded material. So as you get more magnetic loading, you would expect that the loss tangent, when it increases, you'd have slightly less efficiency. But the blue line below that is actually the efficiency associated with no vias in the 40% case. So, and return losses are shown over here. For instance, the black case with the 40% vias has a return loss roughly 900 to about 1100 megahertz as a usable band. In terms of principal plane patterns, in this orientation, the H-plane is shown on the left, E-plane on the right. The H-plane, as you would expect, is a fairly broad pattern given the fact that we have a very narrow aperture in the XY plane. The front to back ratio is about 5 dB in all these examples, and peak gains are on the order of 0 dB. The peak gain is actually slightly off broadside, and I'll be able to show you that in another slide. For the case of the slightly longer wires, as we increased the monopole length to 3.3 inches, the efficiency went up slightly. Bandwidth also increased. For instance, here, the black case for the 40% loading goes from about 900 to 1100 megahertz for a minus 10 dB return loss, and the efficiency is well in excess of 30% over that band and wider. So we get several hundred megahertz of bandwidth out of an AMC antenna that's realistically about 1/100th of a wavelength thick in its free space wavelength. So peak efficiencies lie between 30 and 50%, and again, the no via case is substantially worse. Okay. Skipping ahead, I wanted to show you an omega beta diagram. This is a calculation done courtesy of Jim Aberle. He used HFSS, an older version, to calculate the eigenfrequencies. And so here we see that there is a fundamental stop band from about 750 megahertz to about 1100 megahertz as predicted for the case where we had a 50% loaded isoprene. And that is boxed out in the lower left-hand image where we see that the surface wave band gap is reasonably close to the frequencies where we get fairly high efficiency. Okay, so this is really no surprise. This is what we suspected all along, but this kind of confirmed it. Okay. Let me just skip ahead to one of these. For instance, here's a case where we're looking at the gains. This is contour plots of gains. This is what you get out of the CETIMO range analysis, in which polar angle is plotted on the vertical axis, the azimuthal angle is plotted on the horizontal axis, and broadside is left and right, and peak gains here on the order of 0 dB right off of this broadside position right here. So again, the maximum gain in this case is about minus 0.37 dB, and the average gain noted here is also numerically equal to the efficiency, which is about 35%. So I'd like to conclude by showing or saying that these magnetically loaded AMC antennas that were studied in this particular case had a peak radiation efficiency of about 30 to 40%. They have a 10 dB return loss bandwidth, best case of about 20%, on the order of a couple hundred megahertz centered at about a gigahertz for that lower loading case. The total stack up is about 125 mils, so it's in the order of a hundredth of a free space wavelength and thickness, not including the solder. The plus and minus 90 degree reflection phase bandwidth is also about 20%. And to get reasonably decent efficiency, you've got to use the vias. The vias cut off that TM surface wave mode and prevent the losses that that vertical electric field would otherwise create. And we get reasonably good agreement between the frequency range where an eigenvalue simulation predicts a surface wave band gap and where the antennas exhibit their greater efficiency. Finally, this work was a bit dated. It was completed in 2001. The magnetic materials were actually designed 8 years ago, and I never got around to reporting this. But future improvements, if this were to be pursued, would obviously include smaller magnetic particles. That would yield a lower magnetic loss tangent because you'd have less eddy currents. And so that's one of the obvious next steps to try in this research. So with that, I thank you for your attention, and I'll be happy to answer any questions. Well, yeah, it suppresses the TM modes. The TM modes have a very dominant vertical electric field.
And that's coming because of the propagation through the structure?
Well, you excite both TE and TM modes off the surface if you don't have the vias. And what we're trying to do is create electric fields in the gaps, which will launch a leaky TE mode. If the structure were large enough, you could see very strong evidence of a leaky TE mode. But this is a highly truncated structure. And really all we're trying to do is get the gap electric fields to be phased properly so as to radiate and avoid the vertical electric field that we don't need. Okay.
Is there any connectivity in magnetic material?
Well, is there any connectivity within the magnetic material? I think the short answer is no, because the binder is a gum rubber binder, and I think the iron particles were fairly well distributed, so I don't anticipate much. We tried testing with an ohm meter, but we couldn't see anything, so I think the short answer is no.
So if the magnetic material can be used to a higher frequency, maybe now it's only used 900 megahertz, if it can be used 6 gigahertz.
Well, can we use it at a higher frequency? The answer is yes, but one has to scale the dimensions of the the particles. For instance, if you were to use smaller magnetic or iron particles, you could use it at higher frequencies.